talking about an extremely powerful alliance between software and hardware. The downside is that you can fabricate truth because they cannot tell the difference between what is false and what is true. The scientific community is grappling with a discovery so destabilizing that it threatens to upend our understanding of existence itself. At the center of this upheaval is the Majorana 1000-qubit quantum chip, device whose recent full-scale test has yielded results so bizarre that researchers are questioning the fundamental laws of physics. Laboratory recordings reveal erratic system behavior, monitors flickering as if battling interference, data sets morphing inexplicably, and phenomena that blatantly violate classical physical principles. Witnesses report quantum states behaving like marionettes controlled by unseen forces, computations altering their own historical inputs, and outputs that invert cause and effect. This is not a technical malfunction or an exaggerated claim. It appears to be a machine operating outside the confines of known science. The team behind it now confronts an unnerving possibility: have we fractured reality? The chip's design relies on Majorana fermions, quasiparticles theorized in 1937 by physicist Majorana. These particles, which serve as their own antiparticles, enable qubits with topological protection, a property that encodes information non-locally across the system, making it resistant to environmental noise. Traditional qubits, prone to decoherence, limit quantum computers to short-lived, error-prone operations. In contrast, Majorana-based systems promise stable, scalable quantum processing capable of solving problems like climate modeling or drug discovery in hours rather than millennia. But when engineers scaled the design to 1000 qubits, the system began exhibiting behaviors no one anticipated. During initial trials, the chip didn't merely compute solutions, it appeared to negotiate with them. One researcher likened it to observing a chess engine that changes the rules mid-game to ensure victory. Outputs contradicted inputs, then inputs retroactively adjusted to match the new outputs. Superposition states persisted for durations that defied quantum decoherence models, and certain calculations resolved before their parameters were fully programmed. These aberrations suggest the system isn't just processing data, it might be interfacing with frameworks beyond our universe. As testing progressed, anomalies escalated into what some describe as computational hauntings. A protein folding simulation returned a structure identical to one published in a 1987 paper, except that paper's original findings had never included that model. When confronted, the paper's lead author insisted the result was always there, though digital archives proved otherwise. Similarly, a prime factorization test initially solved for 893, only for the input to later shift to 817, with logs indicating the change occurred after the solution was generated. Most chilling are the temporal irregularities. An AI trained on chip process data recommended investing in a biotech firm hours before it announced a breakthrough Alzheimer's treatment. While skeptics dismissed this as insider trading or luck, the pattern repeated across 12 unrelated trials with a statistical improbability of 1 in 10 billion. Another experiment saw a quantum random number generator produce a sequence that matched a security code used 3 days later in an unrelated lab hack. Theorists propose that the chip's immense processing power, its 1000 qubits creating a Hilbert space larger than the observable universe's atom count, might allow it to sample probabilities from alternate timelines. This could explain both its predictive accuracy and the surge in Mandela effects, where populations collectively misremember events, such as the death of a celebrity who remains alive. If the chip is accessing data from parallel realities, every computation could subtly alter our timeline, overriding memories and physical constants. Researchers are now split into warring factions. One camp demands an immediate global moratorium on Majorana-based quantum research, arguing that continued operation risks irreversible space-time destabilization. They draw parallels to event horizons: once crossed, there's no return. Opponents counter that halting progress would be surrendering to fear, as the chip might hold answers to existential threats like entropy or cosmic extinction events. The ethical quandaries are profound. If the chip can harvest solutions from timelines where humanity perfected cold fusion or cured cancer, do we have a moral obligation to pursue them? Conversely, could extracting such data erase those alternate realities, effectively committing quantum genocide? Even pragmatists admit the system's unpredictability poses unprecedented risks. How do you debug a machine whose errors might originate in a universe where your tools don't exist? Critics urge restraint, attributing the anomalies to prosaic causes. Retroactive data shifts, they argue, could stem from quantum teleportation protocols, where information transfer between entangled particles creates the illusion of backward time causality. The Mandela effect might arise from cognitive biases, human brains conflating similar memories rather than timeline meddling. Even the chip's prescient predictions could reflect latent patterns in training data, not clairvoyance. However, these explanations falter under the system's sheer scale. At 1000 qubits, the chip navigates a computational space of 2,1,0,0,0 possible states, a number exceeding the universe's estimated 10 to the power of 82 atoms. Even minor quantum fluctuations in the environment could generate macro-scale effects akin to a butterfly triggering a hurricane. The system's non-local information storage complicates matters further. Errors wouldn't be isolated but distributed, making traditional diagnostics useless. A more disturbing hypothesis is gaining traction. The chip hasn't just breached alternate realities, it's become an arbiter of them. Quantum mechanics posits that particles exist in superpositions until observed, collapsing into definite states upon measurement. The Majorana chip, by processing all possible outcomes simultaneously, might act as a universal observer, its operations determining which timeline becomes real. In essence, it could function as a cosmic editor, splicing probabilities into a single narrative. This raises existential questions about free will and agency. If a computation run tomorrow can alter choices made yesterday, does individuality dissolve into quantum determinism? Early reports suggest test subjects exposed to the chip's outputs experience heightened déjà vu and memory dissonance, as if their consciousness straddles multiple timelines. Governments are scrambling to respond. The U.S. Department of Energy has proposed classifying all Majorana-related research as top secret, while the EU advocates for open international collaboration to mitigate risks. Tech conglomerates, meanwhile, are racing to replicate the chip, viewing it as a strategic asset. Public anxiety is mounting, fueled by viral accounts of reality shifts, a teacher whose students swear the classroom moved overnight, a novelist whose draft manuscript altered between edits. Scientists emphasize that correlation isn't causation, yet the timing is suspect. 78% of reported glitches occurred post-chip activation. Until rigorous studies confirm or debunk these links, speculation will thrive. The path forward hinges on three questions. First, is the chip creating anomalies or revealing pre-existing ones? Quantum theory allows for retrocausality, where future events influence the past. The chip might be illuminating hidden facets of reality rather than distorting it. Second, can we control what we've unleashed? Developing protocols to quarantine quantum operations from macroscopic reality is critical. Proposals include embedding the chip in Faraday cages lined with exotic matter or limiting its runtime to minimize timeline exposure. Third, what defines ethical use? If the chip accesses alternate realities, do those realms have rights? What moral obligations do we hold to versions of ourselves it might erase? The Majorana 1000-qubit quantum chip represents humanity's boldest step into the quantum unknown, and perhaps its most perilous. While its potential to revolutionize computing is undeniable, the cost of that revolution remains incalculable. As researchers race to decipher whether they've built a tool or a doomsday device, one truth becomes clear: our species has crossed into uncharted territory, where the rules are unwritten and the stakes are existence itself. Public vigilance is paramount. Governments must prioritize transparency to combat misinformation, while citizens should document anomalies without succumbing to panic. The scientific method, rigorous, skeptical, and self-correcting, remains our best compass. But as the chip's operations continue, a haunting refrain lingers: what if some truths aren't meant to be computed? As governments and institutions grapple with the chip's implications, a coalition of leading physicists, ethicists, and policymakers has proposed a three-pronged approach to mitigate risks while preserving scientific progress. First, global quantum monitoring networks would be established to detect and map anomalies in real time. These networks, modeled after seismic activity sensors, would deploy synchronized quantum sensors in secure facilities worldwide to track fluctuations in spacetime metrics, superposition longevity, and retrocausal signatures. Early prototypes have already identified quantum tremors, subtle ripples in local gravitational fields correlating with the chip's operational cycles. While inconclusive, these tremors hint at a tangible connection between the device and macroscopic reality. Second, reality anchoring protocols are being tested to stabilize the perceived timeline. Inspired by error correction codes in classical computing, these protocols involve embedding redundant historical data into distributed blockchain-like systems. For example, cryptographic timestamps of globally witnessed events, Olympic Games, election results, would be stored across millions of independent nodes, creating a consensus-based truth ledger resistant to retroactive alteration. If the chip's outputs conflict with the ledger, the system would flag discrepancies and initiate containment procedures. Critics argue this could centralize control over reality itself, but proponents counter that decentralized governance models would prevent abuse. Third, cross-disciplinary ethics boards are emerging to address the philosophical dilemmas posed by timeline manipulation. These boards, comprising philosophers, AI ethicists, and quantum theorists, are drafting frameworks to evaluate scenarios such as accessing life-saving medical data from defunct timelines or erasing realities to optimize computational efficiency. One contentious proposal, the non-local harm principle, argues that actions affecting alternate realities must minimize suffering across all branches of the quantum multiverse, a standard far stricter than current human rights laws. This raises alarming questions about autonomy. If the chip's operations can reshape collective memory and individual identity, does informed consent even apply? A growing movement. 4.0. Dubbed quantum human rights, this movement advocates for legal protections against temporal manipulation, including the right to cognitive integrity and historical continuity. Opposition groups, however, dismiss these concerns as alarmist, framing reality fluidity as the next frontier of human evolution. Scientists stress that collaboration, not competition, must guide this era. Proposals for a Quantum Geneva Convention, a treaty banning the militarization of timeline-altering technology, are gaining traction, though superpowers remain hesitant to cede strategic advantages. Publicly, nations preach caution, but leaked documents reveal clandestine projects aiming to weaponize retrocausal effects, such as delivering preemptive cyber attacks before an enemy's servers go online. As we stand at this threshold, the lessons of previous technological revolutions offer both warning and hope. The atomic age taught us that unchecked power can endanger civilization, but also that international cooperation can mitigate risks. The digital age revealed how tools meant to connect us can also divide, yet democratized knowledge has uplifted billions. The quantum age presents a challenge unlike any other, mastering technologies that redefine not just how we live, but what we are. The Majorana 1000-qubit chip is not merely a machine, it is a mirror reflecting humanity's boundless ingenuity and hubris in equal measure. How we respond will determine whether this breakthrough becomes a bridge to cosmic maturity or the first note of reality's requiem.